Good morning, physics class. So right now we're going to talk about mass. So as you see, Ian has a basketball and a baseball in his hands. The difference is the mass. The basketball, not just because of size, but it has more mass than the baseball. The basketball has a lot more mass because it has more matter inside. There's a lot more inside the basketball than there is inside the baseball. And that's why the basketball has a greater mass. So now we're going to talk about acceleration, and Ian is going to show off his athleticism and run for us. Yes. So right now Ian's accelerating towards the fence. Now he's turning, another form of accelerating, and now he's running and he's slowing down, decelerating, giving you the 1, Ian accelerating, one form of acceleration, 2, Ian turning, another form of acceleration, and 3, Ian slowing down, which is the third and final form of acceleration. Now, Ian will throw a baseball, demonstrating force, a push or a pull. So now Ian will throw the baseball. Here Ian threw the baseball, and he pushed it forward. So he was the force that was acting on the baseball that made it go forward and hit the net. Okay, so now we're on to equilibrium. Equilibrium is when an object is, static equilibrium is when an object is not moving and it has no acceleration. For example, the ball sitting on the court. It's not moving and it has an acceleration of 0 meters per second squared, giving it a velocity of 0 meters per second. Here, we are going to roll the ball and demonstrate kinetic equilibrium, which is an object moving at a constant velocity, which means that it has no acceleration. So Ian will now roll the ball. This is a form, as it comes to me, of kinetic equilibrium. It eventually does slow down because of the friction decelerating, but there is a time where the ball moves at a constant velocity, giving it kinetic equilibrium. So now we're going to go into some of the special forces. We're going to talk about two forces right here, the normal force and weight, which are both special forces. So now Ian will drop the ball. Ian dropped the ball. So right here we have weight acting as a force. Weight, also gravity, which is the pull which is like pretty much gravity acting on an object in accordance to its mass. So Ian just dropped the ball. That is weight. Gravity pulled it to the ground, and now it stays on the ground. We also have normal force acting here. So we see the ball is not moving, it's just resting on the ground. This is normal force. Normal force is the surface, which is the court, pushing up on the ball, holding it upright. So there is gravity acting down, and it's pulling it down to the ground, and then normal force, the court, keeps it up, so it pushes it up. Alright, so now we're going to talk about coefficient of friction. So we know what friction is. It's it's the resistance to motion on a surface. So now the coefficient of friction. Ian will roll the ball along the court. Okay, so the ball's rolling. It's going to eventually slow down. Alright, it's slowing down. Okay, it hit the fence, but it has come to a stop. So the coefficient of friction wasn't very much here because it kept rolling, and you had to use the fence to slow it down. So the coefficient of friction wasn't very much here. Now we will go roll the ball on the grass, and we will compare the coefficient of frictions. Alright, so now Ian will, once he gets to his spot, Ian will now roll the ball. Okay, see, he's rolling on the grass. Alright, now if you were to compare the distances, the ball that Ian rolled on the court rolled much farther than when he rolled it on the grass, giving the same push each time. This is because the coefficient of friction is greater on the grass. It's a rougher surface with more bumps, and therefore it slows down, but on the court here, it's a smooth surface, so it has nothing really in its way, but friction will eventually act. But the basis of it is there is a greater coefficient of friction on the grass than there is on the court. Welcome, physics class. This is our guest star, Murphy, Ian's dog, and Murphy's going to help demonstrate tension. So, right now, Ian has a leash around Murphy, and it leads from Murphy to Ian. See how the rope is taut? This means that there is tension on the rope, pointing from Ian to Murphy. Ian is holding Murphy back, and the rope it's almost completely straight from where Murphy is to where Ian's holding the other leash. So the tension points from Ian to Murphy. Murphy can't really move much. He can't really move forward without Ian walking forward with him. So this is a demonstration of tension, shooting down the rope from Ian to Murphy. Okay, class. I am now going to demonstrate Newton's first law of physics. The first law of physics is an object in motion stays in motion unless acted on by a net external force. So, for example, we have the Arnold Palmer bottle sitting on the table, or I guess standing on the table because water bottles can't sit. So it's standing on the table, and it's just going to stay here unless acted on by a net external force. Maybe if I hit it, real hard or something, I throw something at it. Unless a net external force acts on this water bottle, it's going to stay here forever. So, a net external force will eventually act on it, but unless I hit it or a net external force is acted upon it, this Arnold Palmer bottle is going to stay standing here forever. Hola, clase. We are back with Newton's second law of physics. So Newton's second law of physics states, is acceleration equals force over mass. So acceleration is directly related to force and inversely to mass. So therefore, if you had a greater mass, it would require a greater force to move it. So here we have an example. Two identical Arnold Palmer bottles, except on the right, this bottle is full of water. On the left, this bottle is empty. Okay, so now, to demonstrate Newton's second law, I will push both of these Arnold Palmer bottles and we will observe what happens. So I'm going to give this a light tap, and that falls over. I'm going to give this the same tap. It doesn't fall over. It just kind of moves along. This is because this Arnold Palmer bottle that's full of water has a greater mass than this Arnold Palmer bottle that's empty. So, with a greater mass, like I said, you need a greater force to move it. So, pushing this lightly might do the trick and push it. Pushing this as light, it won't move it. It's gonna require a greater force. So, compared to these two, now we'll do one final experiment. So I'll hit them both hard. I hit that, okay. So I hit that, and then I'll hit this with the same force. I noticed it didn't go as far. The empty water bottle went off the table because I hit them with the same force, but the empty bottle went off the table. The one with water did not, but that is because this has a greater mass. So with a greater mass, there's a greater force. Less mass, less force. Alrighty, class, we're back with Newton's third law of physics. To start off, I'll give you a little definition from the book. For every action, there is a reaction. This is Newton's third law of physics. So this is the action-reaction pair. So, let me give you an example first. Okay, so see this Arnold Palmer water bottle standing in front of me? I'm going to kick it. Okay, so I just kicked that water bottle off the table. There is an action-reaction force between these two. 1, my foot hitting the water bottle, and 2, the water bottle hitting my foot. Alrighty, class, we're back with Newton's third law of physics. So right now, I'm going to give you a definition of the third law of physics, which is for every action there is a reaction. So this is the action-reaction pair. So I'll give you an example first. There is a Arnold Palmer bottle sitting in front of me, and I'm going to kick it lightly, not too hard. Okay, so I just moved that bottle. There was an action-reaction pair between my foot and the bottle. 1, my foot hitting the bottle, and 2, the bottle hitting my foot. This is, so this means that the forces are the same. So when I hit this with my foot, I hit it, but the bottle hits back. So the forces, they equal each other. It's the same thing as if Mr. Lau gave a great example in class. If you were to punch somebody, if you were to hit someone in the head, your fist hitting their head is one reaction of force, and then the force of the head hitting the hand would be the other reaction force. So you need two objects that will react on each other when a force is exerted. Newton's third law of physics. Alright class, so right now we are in my car, my Jeep, and we are going to talk about static and kinetic friction. Alright, so right now Ian is going to start pushing on the car. So it's static right now because he's trying to push. Now he's pushing, and now it's getting to a... Okay, so now he's moving. So now this is a kinetic friction. Alright, so to break it down, Ian was pushing on the car and it wasn't moving. And this is static friction. So he's pushing, he has to get a greater push to get it moving. Then once it's moving, he doesn't have to give such a great push, which would be kinetic friction. So, like I said, when Ian was pushing before the car moved, that was static friction. And now the car is moving, it is kinetic friction. Alrighty guys, thanks a lot. Alrighty class, thanks for being so attentive. We've got one more thing to teach you, and then we'll be on our way. So, we have an Arnold Palmer bottle, once again. The difference between the mass and the weight of this bottle, they're very different things. So one, the mass is how much matter is actually in the object, compared to this paper on top, the plastic, the water in there, all those particles, everything actually in this bottle is the mass. That's what makes up the mass. The weight is much different. The weight is the pull of gravity on this object. And so with an object with a greater mass, you're going to have a greater weight. Same with a smaller object. If you have a smaller mass, you're going to have a smaller weight. So, like I said, mass never changes, but weight does change. Here on Earth, weight is a gravity or pull that pulls us to the ground. So if you were to drop this heavy object, as opposed to a object with a lighter mass, the heavier object would have a greater weight. But, let's say if we're in space, we're with the stars and the moon and everything, the mass of this Arnold Palmer bottle will be the same up in space as it would be on Earth, but the weight's completely different. There is no gravity in space, so this would just float. It would have no weight, or maybe a little bit, but it would have much less weight than it would on Earth, because the gravitational pull, or the pull of this down, is not near as great as in space as it would be on Earth. So the two big things are mass is the matter, everything inside this water bottle, the paper, the plastic, water, etc., and weight is the force that wants to pull it down to Earth. Yep, so thank you very much for watching, everybody. Hope you guys learned a lot, and physics is fun.